A warm welcome to all. My name is Wilfred Thomas. Today we are going to talk about atomistic origin of the elastic behavior of materials. So before going into the session, let me give you an introduction. So whenever we look into our surroundings, we can see that all the systems in the universe are preventing the change. So whenever there is a change, it will oppose it. For example, you see the inertia of mechanical systems. So the inability of the system to start moving or the inability to come into rest, it is known as inertia. And when you observe the chemical systems, you can see the equilibrium. So what is an equilibrium? The chemical equilibrium. So during a chemical reaction, whenever it is reaching an equilibrium, whenever the rate of forward reaction will equal to the rate of backward reaction, then the system won't progress at all. So if the user or us are introducing any change into the system will prevent it, or the system will oppose it. Similarly, such an analogy can be used here in this particular topic. So whenever we are applying a force into a material body, we can see that a kind of force is opposing to the applied force. So the applied force and this opposing force that is developing inside the body, these two are in the opposite direction. So the system is trying to attain equilibrium. So all the system around us is trying to attain equilibrium. So by attain equilibrium, it can attain the lowest possible energy or stability, in another words. So the elastic behavior is also indicating that the system is trying to achieve equilibrium. When the word elasticity comes into our mind, the first thing we remember is the elastic material like a rubber band. So whenever we stretch it, it will try to regain its original shape or size. So the behavior is known as elasticity. But sad to say, the rubber band or this kind of material, this is another category of material known as elastomers. It's not an elastic material, it is another class of material. So that we will learn in the next session. So the concept of elasticity, it is very complicated one, it is not easy one. So the preliminary concept of elasticity was introduced by the famous scientist Augustin Cauchy in 19th century. So why the body is showing elasticity? So what is elasticity? So consider that we are applying a given force into a body. It will get deformed, the shape, the size, the length or the volume. Any one of these quantities, it will be varied. So the system will try to regain its original shape by introducing another force inside the body which is opposite to the applied force. This internal force is known as the restoring force. So the applied force and the restoring force, these two are in the opposite directions. But why this restoring force is developing in a body? To understand how this restoring force is developing inside a body, let us first deal about how the chemical bonds are building up or it is formed in a given material. So why two atoms are involving in bonds, chemical bonds like ionic bond, covalent bond, coordinate bond, metallic bond, like that. So why they are involving in chemical bonds? To gain stability. So for example, consider the atoms of sodium and chlorine. These two atoms are unstable in the atomic sense, because in sodium the electronic configuration is 281. The extra one electron is an unstable one, and similarly in chlorine the electronic configuration is 287. So if the chlorine gets an additional one electron, it will get stable. So that is how these two elements are performing an ionic bond. So by exchanging one electron from sodium to chlorine, these two species attains the stable octet electronic configuration. So whenever they are forming a bond, they are approaching to each other. So consider two such atoms, an atom A and an atom B. Whenever these two atoms are coming to each other, a kind of attractive force develop in it. An attractive force, F attraction. So whenever they reach in an equilibrium position, let it be a particular distance. This is R0 distance. At this distance, the attractive force between them, F attraction, and the repulsive force between them, the repulsive force between the positive nuclei and the electrons. So these two get balance each other. So in magnitude, this attractive force and the repulsive force will become equal. And in if we are dealing with the direction, then let me introduce the vector notation. So the attraction force will be negative repulsive force. So as these two forces are balancing each other, they will attain an equilibrium distance. So the force between them, or the energy at this equilibrium distance, the energy can be denoted by, it can be represented by U at a particular distance R, that can be written as minus A divided by R raised to M plus B divided by R raised to N. Here A, B, M and N, these four quantities are constants, and this R is the interatomic distance. And you can see that there is a negative sign with the A and a positive sign with the B. So the first term, it represents the attractive force, or the energy corresponding to the attractive force. If there is an attractive force, the energy between them, the potential energy between them is negative. And so this is attractive term. And the second term, this is a positive energy. So this is a repulsive term. And we know the fact that a system will attain equilibrium whenever the energy associated with it is the least possible one. So whenever this value, this potential energy, is the least negative one, the most negative one, then the system will be in equilibrium. So at equilibrium distance, the force between them will be zero, and the potential energy will be the most negative one. So let me just draw the potential energy and the interatomic distance graph of such two atoms. Here we can see two graphs, that is corresponding to the two atoms we drawn in the previous session. So here in the first graph, it is the potential energy versus the interatomic distance graph. So here we can see that as the distance decreases, whenever the distance between two such approaching atoms decreases, the potential energy also decreases. Then at a given particular point, at a given particular interatomic distance, this distance is the equilibrium interatomic distance. At this distance, the potential energy will be the least negative one. At this distance, the system will be in stable equilibrium. Then if we decrease the distance further, then suddenly the potential energy drastically increases. So at this portion, from this particular R0 up to 0, then the force between them, the energy between them will be positive. So it is showing this region is showing the repulsive force, and this region showing the attractive force. So at this negative, the most negative potential energy point, the force will be 0. Here the force is 0. So here also the distance is R0. Then at the right side or the left side, the force is not zero. So the system is not equilibrium. The net force in the atoms is not zero. So at the right side, the force is attractive. At the left side, the force is repulsive. So below, the force is repulsive, above, the force is attractive. So this R0 is the equilibrium interatomic distance. At this distance, the molecule or the system of atoms will be stable. And the potential energy can be represented by, as I told before, by this equation. And the force can also be derived from the potential energy. Like it is the distance derivative of the potential energy. So the force is equal to du by dr. So when we differentiate this term with respect to r, we will obtain this term. So from this force, we can derive the stiffness of the bond between two such atoms. The stiffness or rigidity of the bonds between two such atoms which made a chemical bond can be represented by stiffness F is equal to the distance derivative of the force between two such atoms. And we know that the F can be written as du by dr. So all these terms, all this expression can be written in the form of a double differential, the double differential of potential energy at R equal to R0. So from it we can see that the stiffness of the bond between two such atoms is directly related to the interatomic distance between such atoms. Now we are going to see how the deforming force is inflicting a restoring force in a given material body. Let's see what is the root cause of the restoring force developing in a material body. So consider a crystal system in which atoms, molecules or ions are arranged in a regularly manner like this. So here tiny springs are arranged in between such atoms or ions. So these springs are representatives to the chemical bond, because springs can be analogous to this chemical bond, because we know that for a given spring at its equilibrium distance, at its equilibrium length, it will be stable. So when you just introduce a force, a compressive force or a tensile force, we will just stretch or compress it, you can see that it is preventing the change. It is trying to attain the old equilibrium state. So it is very similar to chemical bonds, because whenever you are increasing the interatomic distances or decreasing the interatomic distances, the system is preventing it, because at the R equal to R0 position, at this distance, these two atoms are in the lowest possible energy or in the stablest position. So these bonds can be represented as springs. Okay, then consider the situation in which you introduce a force. So by introducing a force, you are just compressing it or just elongating it. So you are literally increasing the intermolecular forces or decreasing the intermolecular forces. So we can imagine that what is going to happen next. The system will try to attain the equilibrium. So if you are introducing a compressive stress, a compressive force, so the intermolecular distances will shrink. It will be decrease. So it tries to increase to its original R0 value. So it will apply a force which is opposite to the compressive force. So if you are introducing an applied force like this, so the spring length will be decreased. So it will inflict a force, an internal force in the opposite direction. The F internal, that is the restoring force. And suppose that if you are stretching it, if the applied force in the opposite direction, applied force. So what is happening here? You are stretching it. So the bonds between the atoms will be elongated. So the system will try to decrease to the original R0 value. So there will be a force introduced in it in the opposite direction. So it's just a play of stability. The system is trying to achieve stability. So this deforming force is directly depending on the interatomic distances between the atoms, and it is also depending upon the crystal structure of the material. So whether it is regularly arranged like in a metals are also crystals, or in NFL crystals or diamond, or whether it is an amorphous material like glass or clay like that. So it is depending upon the nature of the arrangement of atoms in the given material. So the elastic behavior, the tendency of a system to achieve its original state upon the removal of the deforming force, it is entirely depending upon the atomic arrangement in the given material. So by this I am concluding this session. Thank you all.